Hello. 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 Wait, can you hear? Am I? Hello, Yanelli. Hello, Chastity. Hello, Skylar. Ah, there. Good afternoon, Vanita with the double. Good afternoon. Okay, I'm going to the chat now. Wait, why do I hear? Oh, weird. I'm sorry. Hold on. Okay, that's weird. Sorry. Good afternoon, Vanita. Good afternoon, Chastity. Good afternoon, Ariana. Oh, there's the Kaya with the Kaya. Good afternoon, Sydney. Good afternoon, Natalie. Hello, direct chat person. Good afternoon, Yanelli with the double. Good afternoon, Kaya with the double. Good afternoon, Gabriella with the Gabriella. Good afternoon, Brian. Okay, wait, is that? Did I say Mary? Okay. And thank you for your service. To anybody to whom that would apply, I should thank you all for that, Moral. There's probably more of you that deserve that thanks than I even know. And I'm not being sarcastic at all. It's just like it's overwhelming to even know that. Um, yeah. Okay. So, oh, good afternoon, Miriam. Good afternoon, Miriam. Okay. So we're gonna get rolling. I am Yes, we're gonna get rolling on that. What's on the board right now? That's a little intimidating even to me. 'Cause it's kind of messy. I'll explain in a second. But a couple of logistical items. First of all, so I wasn't here last Monday, but then I saw it's been a little bit of a thing. So if you are still missing some documents from me or some points, yes, you are, and that's on me. Not you. It's not personal. I'm a little behind, is basically what I'm just saying. This happens to me or from me. So I'm aware and I'm catching up and I apologize. Um, but I'm aware. Uh, and I'm talking about, game stuff, game and homeworks and things like that. And they're all there and they're coming back. Um, but then also, we're going to get back to the Doppler effect today. Substantively, what we're going to talk about is the Doppler effect. We're going to finish talking about the Doppler effect today. Um, but you may have noticed a posting in Google Classroom that referred to a midterm exam. So, yes, it's time that we have to start dealing with that reality. I don't love dealing with that any more than you do. I mean, I probably dislike it slightly less than you do, but in any event, it's a reality that we do need to have a midterm and a final exam. Some of you have been through this experience with me before, some of you have not. Um, we will talk in more detail as we get closer to the actual midterm. But the one thing I want to confirm today, or I want to confirm, can you confirm that you see in Google Classroom a posting that tells you the logistics? Like you should see a posting in Google Classroom that says that the midterm exam will be due Wednesday, April 2nd. Do you at 3:05 p.m. Is that posting there and is that what it says? Can you confirm or deny, please? You see the announcement? Yes, thank you. Okay, yes, yes, yes. Okay, great, great. Thank you, thank you. Okay. So, great. Thank you. And thank you, Sydney. I see that. Okay, thank you. Okay, so I don't want to over talk about it today. And again, and I would hope, well, the main things to say right now is that um and I know that some of you have an orgo thing that's, I think you have an orgo exam, some of you on April 1st, which is very unfortunate and what I sort of try to avoid. And if enough of you privately tell me, even in direct chat or later, if enough of you privately tell me that it's all a big, big orgo conflict, or if there's a big conflict across the board with enough of you, I will readjust. But of course, there's always a conflict with some things with some of you. Um, so there's only so much we can do. But but as it stands now, as I understand now, um, your midterm in this class will be due 3:05 p.m. Wednesday, April 2nd. The reason it's Wednesday, April 2nd, honestly, it would have been Monday, March 31st, but it turns out we don't have school that day, or I think. Um, so yours will be due Wednesday the 2nd, and it's actually a little bit of a bonus to you. I'll tell you one of the advantages, even if you do have an orgo conflict or something, one of the advantages of this timing is that what I'm not going to change is the fact that I generally post these exams on the prior Thursday. And that's what I'm doing for this one. In other words, just to quickly give you the logistics, the exam itself will be posted no later than 8 p.m. Thursday evening, March 27th. I mean, and again, hopefully that's what the posting says. I mean, hopefully that's what this announcement says, and tell me if it doesn't. But so you'll get the exam posted Thursday night, and then you have almost a full week to do it. Okay, again, that's a little longer than I normally would like to do, but that's the way, but that's the way it is. So you have a week to do it. And hopefully that too will allow you to manage your time. Like even if you are during that week studying for another exam, hopefully that allows you to distribute things so you're not doing everything on one night. Um, for those of you who don't know, when I say that the exam will be posted Thursday night and that you then have a week to do it, I mean what I'm saying. That is, if you don't do my exam under test conditions. I call it an exam because it is an exam, because it counts as an exam, and because it examines whether you understand the material to that point. But really, it's much more of if you want to think of it as a paper or a project or a presentation. And again, I will speak about more of these details as we get closer. But just to be clear, my exams are take home, non-timed, non-monitored, open universe experiences. And that in other words, many of the things that you would normally consider cheating are not cheating on my exam. I'm telling you to do them. And it's not because I'm an idiot. I mean, I might be an idiot, but that's not the reason for this. Um, Again, at the risk of rabbit holing, I'm saying that once the exam is posted Thursday night, then you use whatever resources you want, including one another, including your aunt who got a Nobel Prize in physics, including definitely the MSRC, which I'll address in a moment, including your lab instructor. Like you find out whatever you need to find out to learn the material. Um, and then you present me with a thorough, complete, super clear, super well presented document that walks me through the full 5 steps. And that's like a minimum, all the steps of every problem that you're working. And you guide me not only from beginning to end of the solution, but with a full explanation that makes it totally clear that you understand what you're doing. You're breaking your work down into as many teeny tiny steps as possible, and you're using as many colors as possible, and you're interplaying diagrams with annotations, with equations, right? I mean, I'm not trying to scare anybody. I'm saying though that in the end, what you're giving me is not answers. You will already know the answers, and you'll know that I know that you know the answers, or at least you have access to them before you even do this thing. So it's about process, it's about presentation, it's about walking me through the physics as you best understand it. Okay, and again, I know some of you have experienced this already with me, but some of you have not. Um, and as in terms of a guide as to what to expect or what it looks like, or what the exam would look like when it's posted Thursday, I hope it's sort of clear. There's already an exam in Google Classroom, like the midterm exam from last semester or the semester before or something, which is right now the closest possible approximation to what you should expect for your midterm. You could open it at any time and start, and I highly recommend that the way you study or prepare is you just like practice that thing and practice with your friends, or make friends, colleagues, but practice with your enemies if your enemies are better at physics than you. Whatever, bake them brownies. I mean, but seriously, like the way to prepare yourself for the actual exam is to start getting used to and trying to rock the practice exam, or at least the questions in it that we've covered thus far. As we get closer to the actual exam, believe me, I'll keep checking the practice exam and seeing like where we are in relation to it. And as we get closer to our exam, if I feel that we've emphasized one thing more than we did last semester or one thing less, or we haven't got, I will adjust your exam so it reflects like what we as a group have done. And I will therefore update and adjust your practice exam accordingly. Like so that if I make any changes to the practice exam, it's just to make it a more and more accurate representation of what you should expect on Thursday night, March 27th, when this thing gets posted. Okay. So, and again, I will answer more questions as we get closer. I'll address material more directly as we get closer. I mean, as we get closer. But I just want, that's the basic thing of what to expect. And if I didn't remind you already, I believe you've received emails from the MSRC. The MSRC this semester is actually holding like a review session or like a exam prep session for you guys, which is awesome. And the people that are doing this is like they didn't used to do this in the past, but the people that work there now are like super cool and devoted. And so they already have the practice exam from me. If I make updates to it, I'll tell them, but they're just going to literally like they're not going to waste your time. They're going to go over the practice exam as a way of preparing you for the real exam. So, I mean, that's not, none of this is required, but these are my recommendations for preparing for the actual exam. There was one other quick thing, and I will look in the chat in a second. I'm sure or I think there's questions, but as far as and your actual exam will not be identical to the practice, but it'll be really close. I mean, I'll be more detailed about that too. But really, the one of the ideas behind this whole method of having super take home, super open universe, and with a practice document in advance is that I don't think physics is easy. I mean, physics is already hard, but what we don't need is the unnecessary surprise stress elements of exams like that. I'm trying to get rid of those elements. I can't get rid of the innate challenge of physics. But we don't have to play games about like me trying to hide the ball and you trying to guess what I'm going to put on it. Like none of that is like the point. The point is physics is hard. The point is that you're going to show me how fluent you are becoming in the language of physics. So you're going to write, an extensive physics essay, which is not literally an essay, but which is your solutions to the problems. You're going to show me by breaking it down step by step. Like anytime it comes into your mind, should I actually include this in a step? Like, I mean, I divided both sides by 2. Should I like literally write that as a step? The answer is yes. If something occurs to you as something you did in your mind, write it down and say, then we divided both sides by 2 or whatever. The more small steps you can break everything into, the more you convince me that you actually know what you're doing. The metric is at any moment, ask yourself, if we were sitting in my office and I was asking you questions like, how did you do this? How did you do that? Like if you could answer them, then you're making a totally authentic and convincing document, which is the goal. Okay, I'm going to shut up in a second. Again, we'll talk more about, I'm just trying to give you the overview. I'm not trying to scare you. I mean, the good news is it's really a test. It's almost more my exam. Well, I like to think that my exams are kind of more a test of authentic progress in the learning of the language of physics than anything else. I.e., there are some of you who still feel shaky about physics concepts or even physics information, or there are those of you still feel shaky about like my communicate, like whether I make any sense to you or not. If you treat the exam with care and give yourself time and write like a rough draft before you write a final draft, if you're really careful about it and thorough and give yourself time and approach it as an opportunity to show honestly what you understand and what you don't, if you're honest about it, you can do really well on this exam, even if you're still feeling shaky about certain things. You can do really well, even if a number of answers are wrong. What you can't do is, and people do really well, even in those cases. What also happens, though, just to be clear, and then I'll shut up and look in the chat. There have been people in the past who are used to more traditional exams and stuff, and who to whom this sounds like a joke, like the idea that you could just take it home and all that. So there are people, have been people who just like put a bunch of answers down or get a bunch of things from the web that all make sense on the web, but they didn't process through their own brain. In other words, there are people that have done things where they get the physics answers correctly, but the process is not authentic, or they get their friends to help them a lot, which you totally should do. But then instead of having their friends help them get better at it, they have their friends essentially write it out for them, or they write out what their friends wrote. And I'm telling you, that doesn't work. It's not possible to do really badly on this exam if you have a lot of integrity and authenticity. Really, it's very possible to do very well, even if you feel insecure about physics. But it's not possible to do well on this exam by trying to fool me with information that's just grabbed from the web or from someone else. I'm personally a little bit too um I mean, I'm far more fluent in the language of physics than the level of fluency that I'm asking you to demonstrate. And I'm not saying I'm perfectly fluent at all, but I am more fluent than the level of fluency that I'm asking you to demonstrate. And therefore, I am fluent enough to know when somebody is actually speaking the language to me as best as they can versus when someone is just copying information to me. And I'll just leave it at that for the moment. But okay, so that's a timing. So oh, and last thing before I look at the chat, because this is usually a question too. As we get closer, I'm going to try to give you as many sort of solutions or answers to the practice exam sort of as I can as I go. But I'm not going to answer everything on the practice exam. It's not going to be one formal moment where I give you an answer key to the practice exam. That doesn't happen because if I did that, if I literally just handed you an answer key to the practice exam, there'd be very little for you to do on the actual exam. Like part of this is you figuring things out on your own. However, I highly recommend that you go to the YouTube channel. There's tons of past videos of mine that are called like MT walkthrough or pre-MT walkthrough, MT meaning midterm. There's plenty of videos where I walk through the practice exam or the exam itself, and I mean, you're welcome to watch, find those, and then share them amongst yourselves. Whatever you could find is great. I'm just not going to spoon feed the answers to you because I'm not. But I will give some answers and some solutions in class as we get closer. And your lab instructor might, and that's fine. And the MSRC might, because they might still have them from the back. That's fine. I, but I just have to manage my time. Okay. So that's the overview. And I'm going to look at the chat right now. We're going to go on. This is not the last time we're going to talk about the exam before it happens, but this is the overview. If there's basic questions or concerns about the overview, like the logistics or the basic expectations, I certainly am happy to hear them now. But in terms of nitty gritty, we'll do that as we get closer. Okay, so I'm going to look at the chat. Oh, I'm scared already. Oh, wait. Wait, that's a great question. I'm sorry. Oh, that's my mistake. Okay, sorry. Yeah. Oh my God. Okay. And you're gonna, all right. So someone in the direct chat, I almost wish it was public because you should all thank this person. So someone is privately mentioning that the homeworks are all crowded together due next Monday. And then there's one that's even due the day of the exam. Is it possible to get those spaced out better? Yes, absolutely. Thank you. I meant to look at that and I haven't in a while. I will rejigger the homework so that it's not in conflict with your exam. Yes, I will do that. I may or may not even do it right now in a minute, and you can remind me again if you don't see me, if I don't remember, yes, I will reconfigure the homework so it's not in conflict with your exam. I'm happy to do that. Let me also point out that homework 5A and homework 5B, but they are both due on the same day. That I do know, and that looks very tight, but they are both like optional. Now, I mean, all the homework is optional in a way because it's just for points that you want to get, and like if you don't, whatever, all the homework is optional in a way, but homework 5A and 5B are specifically optional in that. And it's so optional that the reason they're both due on the same day is I kind of recommend to any of you that's interested in that you maybe do one or the other, but you need not feel compelled to do both. What's making them like even so, I'm not going to hold it against anybody. If you don't do homework 5, either of them, I won't even psychologically hold it against you. They're really good to do especially the one that's called tone is particularly for those of you who are quite possibly like thinking of taking the MCATs or things of that nature, right? Specifically the M, and there always is some of you, and there's sort of more every year. Um, Homework 5A, and you'll get points, of course, if you do it, like, whatever. I mean, it'll help your grade, but it won't hurt your grade if you don't. If you might take the MCATs, you really might want to do homework 5A because it's very MCAT-y. That's all I mean, and sidebar on that, the MCATs are like a whole thing. And I know it doesn't apply to many of you, but any of you who it might be applying or things of that nature, or even like the GRE, talk to me personally when this class is or when it's relevant as to like guidance and coaching how to approach those standardized tests because they can be scary at first, but there is a way to approach. They can look very different from the way we do things here, but they're not. But anyway, so homework 5A is sort of good practice if you're going in that direction with your life. Homework 5B is more relevant directly to this class. But yeah, anyway, but they're both more, but what's really making them optional, A and B, is that they're not on this exam. That I can assure you. The material that is being asked in homework 5A and 5B, they're in and of themselves. They're things that, so technically, like they're, so that we've been exposed to them. Uh, well, certainly 5A is so that we've been exposed to it, but it's not on this exam. And 5B, is definitely relevant to this class, but won't become relevant until the final exam. Okay, so, but yeah, anyway, I don't know if that clarifies it, but yes, I will reconfigure the homework so they don't conflict. And no matter what, when in doubt, once it starts getting closer, if you ever have a moment where you're deciding whether to practice for the exam or do a homework, practice for the exam. And just write me a note saying I'm prioritizing the exam right now. Can I have an extension or whatever? And I will, okay, and I will. I mean, but okay. So thank you. If I don't fix it in a second, please remind me. Okay, wait, and there's a direct chat. Hold on a second. Hold on one second. Okay. Whoop. Okay. Oh, okay. So you said thank you. Okay. All right. Let me forgive me, but I'm sort of afraid. That's such a legitimate thing about the homework. Give me 2 seconds to fix that right now, if I can, because I'm afraid I'll forget. And it's so give me a second. And maybe while I'm doing that, like look over the posting or see if check out the whatever. Just make sure you're clear on this. Hold on. Oh, I see what you mean. Well, oh my God, yeah, homework 6, that's a disaster. I'm definitely changing that. Okay. Um, okay. Um, thank you for bringing that to my attention, the homework thing. So I just changed homework 6 for sure. That was a good, I mean, that was necessary. Um, for, well, all right, let me think about it. One second. I'm thinking about the homework 5 thing. And I just changed homework 7 also to reflect the change in homework 6. Homework 5, let me think first. Um, I am going to, okay, I'm really glad the person brought that up. And obviously I don't want to spend all period on this, but I also don't want to forget. So what I'm going to do right now, I will move the homeworks 5 so that I appreciate the idea that I'd rather your brain just be psychologically clear to deal with this exam as we get closer. Right. And since homework 5 is not relevant to the exam, I'm going to move homework 5 now to, I will tell you that that will stack homework 5, both of the homework 5s. They will stack them close to homework 6, but it'll still all be after the exam. And homework 5 is optional. So I think it'll still be better for everybody. I mean, it's still gonna be a little bit of a crunch, but I think it's better for the crunch to be after the exam. I appreciate the point. And again, if when in doubt, please remember, I think it says, but if you have to like triage something, just forget homework 5A and B. And I won't, because we're not like, well, certainly 5A in particular. Um, yeah, I mean, it's very possible that neither one of them will we ever go over in class. That's what I sort of want to honest, I just have to admit that to you. So like, but you get points for doing them and you would be more educated if you do them. But anyway, all right, so I'm going to change those right now and then I'm going to shut up. Um, let me see. What? Oh, okay. So, okay. Right, right. Okay. So, and I'm going to ask you to check in a second, particularly the person who, but anybody, can you check? I believe, I believe it should all be good in 1 second. Yes. Can any of you right now just do a quick check of the next upcoming homeworks that they should be all due after the exam and uh no two should be on the same day except for 5A and 5B could be on the same day. And I will check with you in a second. Okay, yeah. So from my point of view, it looks right now. Let me see. What do you say? You say yes. Okay, great. It changed. Yeah, it changed. It says episode. Okay, great. Thank you. Thank you. All right. No, really good point. All right. Thank you. Okay, so that's the deal with that. So now back to like physics. So So the big conclusion now, hopefully, you were in class last Wednesday, and hopefully, maybe you even watched, well, hopefully, definitely, you did or will watch the video from the other class from last Wednesday. The big takeaway. Well, wait, have I? Oh my God, hold on 1 second. Sorry. Yeah. Oh, wait. Okay, sorry. I'm totally disoriented, but I think, okay, you're going to correct. I, I believe that if there's one thing that was a major takeaway of the video that you watched before last Monday, you watched a video. Correct me if I'm wrong. I'd like confirmation of this. I believe that a big takeaway of that video that I even believe some of you were asking me questions about last Wednesday, but I believe a big takeaway was that the velocity of a given wave is fixed and constant relative to the wave's medium. I would like some confirmation. I'll say that again, but can you confirm or deny in the chat that this is a constant? Like, I'm not saying that you perfectly understand it, but have you heard this? Like, did I say it in a video and was it emphasized? And did I address it last? I'll say it again. I believe that, like once you do the wave equation, and once you see that the speed of a wave is omega over k, and once you realize that omega is determined fully by parameters, and so is k, I'll say this a different way, but mathematically, if the speed of a wave is omega over k, and omega and k are known the minute you know the material properties of a medium, then that means you know the speed of a wave the moment you know the material properties of the medium through which the wave is flowing. Can anybody confirm or deny if anything like what I just said seems at all even familiar? Even if you don't, I mean, believe me, I'm going to say more about, like, even if you don't understand it, is that a familiar concept? I'm saying the speed of a wave is constant relative to the wave's medium. Oh, cool, cool. I love someone said I found it in my notes. Okay. Somewhat. Well, somewhat is fair. Yeah, I'm not saying could you take a test on that idea right now. But someone said I found it in the notes. That's kind of what I'm asking. Like, has it even come up yet? Okay. But somewhat. All right, but it sounds like it's a little hazy. It's only two people answered. All right. Um, so maybe I need to emphasize this again. Let me I'm just thinking, I don't want a rabbit hole. Um, well, all right, I'm gonna rabbit hole. I'm gonna take a risk here. One second. Okay, this is the 1D wave equation, right? And again, I'm not asserting that this is all totally comfortable to you yet or totally clear, but I am asserting that you've seen this now, like through the videos, through lab, whatever, you've derived this. This differential equation describes any wave traveling through a one-dimensional medium. This piece right here. The V, well, omega over K. In other words, omega is 2 pi over the period. It's like omega is like how many cycles are being performed per every second, per every unit of time. Omega is cycles per time, but measured in radians, so there's like a 2 pi involved. But omega is cycles per time. K is cycles per space. How many crests or troughs there are in a given meter, right? Right? Like this is like, so omega is cycling rate in time. K is cycling rate in space. You put one over the other, if you think, you have like a fraction over a fraction. So the denominator, the bottom, it's like 1/1/4 equals 4, right? 1/1/4 equals 4. The 4 flips all the way to the top. So 2 pi over t over 2 pi over lambda is really lambda over t. It's distance over time. It's literally omega over k, in other words, is literally like it's a speed, a velocity, but speed or velocity of what? Not one of the little oscillating particles. No, 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 not speed along the y-axis, but because that's changing all the time. Like harmonic oscillation, every moment you have a different position, you have a different velocity, you have a different acceleration, you have a different jerk, right? That's the whole point of homework one, is that the things going up and down like this or whatever, their motion is just crazy, a bunch of cosines, infinitely differentiated. But what we're saying is that if you have this, and then you have this, and then you have this, you create this pulse that goes like that goes along the x-axis, right? And that pulse like has has a wavelength between any two successive crests, or a wavelength between any two successive troughs. And if you stare at those lengths, like the distance of those cycles, they're moving along the medium through time. And the number of cycles per time divided by the number of cycles per space is how fast the pulse is propagating along what we're calling the x-axis, right? Like literally, if there's 2 meters between every two crests of this wave, and it takes 2 seconds for you to have to wait from one crest to the next, then that means each crest is flowing along at 1 meter per second. I mean, I just made up those numbers, but you see what I'm saying? So V, omega over K is V. It's the speed at which it's technically called the phase velocity. It's like the velocity of the phase of the wave, whether you're looking at a crest or you're looking at a trough, whatever phase of the wave you're like staring at, the rate at which that flows, that propagates through the medium is this V, is omega over K. Okay, so technically now I'm like reviewing something that I think was said in one of the videos, but whatever. I'm just trying to make it right and stop me if I should, or accelerate me if I should go forward. But here's my big point. My big point is that if the speed, if the flow speed, the propagation speed, if V is omega over K, and what's omega? Like, well, omega is cycling, right? Like I just said, but omega is that rate at which each one of the oscillators, goes up and down. In other words, if each one of these oscillators was a mass on a spring, omega would be square root of K over M, right? Or, for example, what we've been saying about harmonic oscillation that's so deep is that the omega of an oscillator is independent of how the oscillator is set up. Remember, the essence, and this is in your notes, like from like weeks ago, the essence of harmonic oscillation is an angular frequency that is so constant. How constant is it? It's so constant that it doesn't depend on amplitude. The frequency, remember, like the mass on the spring goes back and forth and back and forth, like homework one, goes back and forth and back and forth at a specific rate that cannot be changed by starting the mass over here or starting the mass over here or whatever. The amplitude doesn't matter. All that matters in the case of a mass on a spring is like K and M. Once you know how stiff that spring is, and once you know how heavy that mass is, it's going to go back and forth at a certain fixed rate. That's already interesting about oscillators. That's how oscillators make clocks, because they tick at a rate in time that is independent of space. But now I'm saying, wait a minute then. If the velocity of a wave pulse is totally determined by omega and K, and the argument I just made about omega, we can make a similar argument for K. That is, omega and K are, where'd my set? Oh, these things are fully, these values are fully determined by parameters. What does parameter mean? It means a constant material property. Like again, in the case of a mass on a spring, like how heavy the mass is, how stiff the spring is. Something that you could measure the minute you take these ingredients out of the box, like before that you do anything with the ingredients. So if you've got a wave pulsing through a medium is a bunch of material oscillators, right? What I'm saying, what this math is saying is that as long as you know what type of oscillators they are, as long as you know the mass and the stiffness of each one, or if it's air molecules, as long as you know the pressure and the temperature of the air molecules or whatever, as long as you know the specific defining characteristics of the material through which the pulse is going, then you automatically know the speed at which the pulse will flow. But, well, because I just skipped a step. If you know the material properties, then you know automatically the rate at which each bit of material will oscillate. And if you know the rate at which each one is going to oscillate, omega over k, then according to this, nothing else comes into play in determining V. V is fully determined by omega and k. Omega and k are fully determined by material properties. So that this is why we can say, why we can talk about the speed of sound in air, as though there is one, right? I believe I said this on last Wednesday to answer one of your questions, but I cannot emphasize this enough. Look, I'm trying, but I can't. No one ever talks about the speed of baseballs. I mean, you could talk about this pitch or that pitch or that, but baseballs don't intrinsically have a speed. They could go any speed within reason. But sound in air at standard temperature and pressure goes a speed that we all know, whether we know the number or not, 340 meters per second. Like, because once we say it's air, molecules at standard temperature and pressure, then we automatically know each one of those air molecules is acting like a little mass on a spring with a known K and a known M. I mean, in this case, it's like T and P, but it's the same idea. I mean, literally, it's not just the same idea, it's the same math. So once you know each one of these air molecules is a little mass spring system that has its own effective K and its own effective M, sidebar, that's why on homework 3, like it asks them, it's like this whole temperature system that's oscillating, and then in the middle it says like, okay, imagine the mass of the whole thing is this. Can we pretend the whole thing is a spring with an effective K of how, turns out to be like 8,000 newtons per meter or something. Like, what was the point of that question? The point of that question is this, that no matter what material you have, it's acting like a little mass on a spring. And if you know its characteristics, you know the rate at which this effective mass on a spring is going to oscillate. And then according to this equation here, omega over k equals V, if you know the omega and you know the k by same reasoning, then you automatically know the rate at which the pulse is going to flow through the medium. And there's nothing you can do about it to either change the number or accelerate it or decelerate it or be wrong about it unless you change something in the medium. Like waves will go through water at a certain speed as long as the water is at a certain depth and a certain temperature. Now you want to change those waves. Okay, add salt to the water. But you got to change the water. You can't start wait. Oh my God, the Zoom thing is totally telling me to lower my hand. Okay, it'll lower my hand. 1, 2, 3, 4. Okay. Okay, I'm going to stop. But the key point is if you know the medium, you automatically know or have access to the speed at which this wave will travel through the medium. And it's done. Like that's a property of waves that's not only, to me, super fascinating, but it's also super useful. Like it's like one of the reasons we care about waves. Can I just say that a game that I used to play with my younger son when he was like younger, like if he was bored at the beach or like at a pond or whatever, and we were looking at the ripples in the pond, this never worked, by the way, but he would look at the ripples in the pond, and I would say to him, it's so obnoxious, but I would say, let me know as soon as, like, I want you to watch those ripples and tell me as soon as one of them catches up to another one. Right. And of course, it never happened. I'm a better father than this sounds like. But of course, one ripple never catches up to another ripple. If you think about it, even the fact that you know the concept wavelength, that you understand, oh, wavelength means how far apart two crests of a wave are, that already assumes that there even is a number for that in a given wave. That assumes that that number wouldn't change while the waves travel. And it doesn't. If you think about it, even someone who doesn't care about waves at all or doesn't think about them mathematically, anytime they draw a picture of waves or take a movie of waves or just think about waves, no one ever pictures ripples of waves catching up to other ripples. They always picture all the ripples as having a constant gap between the ripples, right? Like that's just the nature of how we draw them and stuff. Like crest, space, crest, space, crest. And the spaces are always the same. Why? Because what we all unconsciously know, but have never necessarily, but some of us have not like mathematically consciously realized, is that once you have a medium like water, the ripples can only go at a certain speed in that water. So all the ripples go the same speed. So they all just travel in formation. That's what makes them so beautiful. Or part of it. Okay. So I'm getting carried away. But what I'm saying is the speed of a wave is fixed and constant. The speed of any wave is fixed and constant relative to its medium. That makes waves extraordinarily predictable and extraordinarily easy, manageable to work with, right? But then, stop me if this doesn't. So that's a thing. The speed of a wave is relative to its medium. That's what I'm asserting. But now, notice the phrasing. Speed of a wave is relative, is constant relative to its medium. That brings us back to an original understanding of velocity that we've always had, but we've always had through physics 203, but now really have to take seriously here in physics 204. And it's up here. Like I'm saying, I'm reminding you now, we've got to resurrect a concept that I still think is central in any physics we ever do. Velocity is a relation between two objects. It is not a property of one object, right? The Earth to you, in the frame of the reference, in the frame of reference of Earth, Earth is going 0 miles an hour. Like relative to Earth, Earth is going 0 miles an hour. In fact, relative to me, Earth is going 0 miles an hour. And relative to Earth, I'm going 0 miles an hour. And to us both, the sun is going 65,000 miles an hour. I mean, that's what it like seemed, my measurements of the sun across the sky would say that. But relative to the sun is going 0 miles an hour and the Earth is going 65,000 miles an hour, right? And either one is correct. Both are correct. And if you stand on the Earth, you don't feel the velocity, right? Velocity is a comparison between two objects. It's not a property. It's not an objective property of one object. All velocities, in other words, are relative. You can't talk about velocity without having two objects to compare to each other. Hence, whenever you're talking about velocity in a rigorous way where things matter, like physics, it's best. I mean, sometimes we can get away with not doing this, but when in doubt, it's best to put double subscripts on velocities, right? And realize what is being summarized here on the top of the board, what in physics 203 we call the fifth form of Galileo's principle of relativity. Now, again, some of you didn't have me before, so some of you haven't seen it done like this before, fine. But I'm saying Galileo's principle of relativity is that the laws of physics are the same at all constant velocities. And therefore, a bunch of stuff follows, like what I just said, that you could be on an Earth that's zipping through space at 65 and you don't feel it at all. But what also follows is this mathematical way of looking at it. Like there's three little equations up here. They're self-evident once you think about them, but they're really useful in situations such as the Doppler effect. Okay, case one is the one object. So imagine you have three objects, A, B, and C. Object A, object B, and object C. So case one is saying the velocity of A relative to A. The velocity of any object relative to itself is always zero, always in physics, right? Again, this is just like a mathematical expansion of the relational character of velocities. The velocity of an object relative to itself is always zero. And this is like how all video games work, right? Like you're not moving compared to you. The whole world is moving past you, right? And that's not an illusion, like that's not wrong. That's as right as anything else. But then say you have two objects, say there's you and a tree. The velocity of you relative to the tree is necessarily always equal to the opposite of the velocity of the tree relative to you, right? If the tree observes you moving at 50 miles an hour to the east past the tree, then you observe the tree moving at 50 miles per hour to the west past you, right? Like, I mean, I think everybody, right? I'm just reminding you, but these are important for the Doppler effect. The final thing, so it was the object one, one object case, two object case, and now the three object case, a little bit more subtle. The velocity of A relative to C is equal to the velocity of A relative to B plus the velocity of B relative to C. Now, again, you know, some of us stressed hard over this last semester. Some of us didn't. But this can go many places. But in short, what this means is the velocity of me relative to the subway plus the velocity of the subway relative to New York City streets equals the velocity of me relative to New York City streets. That's why I take subways, so that I can sit still and be going zero relative to the seat, and yet have the seat be going 80 miles an hour relative to the streets, so that at the end of the day, I'm going 80 miles an hour relative to the streets without having to put any effort in, right? That's like the whole point of a subway. But it works even in the more complicated case. This concept of this is not because of engines or anything else. This is the nature of velocity. And it works even in cases where none of the numbers is zero, and even when there's angles and stuff. I mean, if I walk backwards on an escalator, right? If the escalator is going up at 5 miles an hour relative to Columbus Circle, but I walk down the escalator at 2 miles an hour relative to the escalator, then I'm only going up at three. Well, you know what I'm saying? Like, in other words, minus signs work, and you can even do this stuff at angles and it'll still work. The velocity of one object relative to another plus the other relative to a third equals the velocity of the first relative to the third. That's the way velocity works. Now, again, that's technically a review, but if it's not, you should think about it, because now we're going to use it. So all of that little box where it says GPR form number 5, all of that is just true about velocity in and of itself. It's fundamental to physics. In some ways, we get used to it, or we got used to it in Physics 203. In some ways, we never get used to it, and it leads to all kinds of cool things, Einstein in 1905 and all this. But it's just the nature of velocity, and it's just always true in physics. But then we come along now in the second box on the board. Now we come along and we've got this idea that velocity of a wave, or the speed of a wave, is omega over k. And another, right, what I was just saying before, and another way of saying that, a totally equivalent way of saying that, is lambda over times f, right? And that also was in the video, I'm pretty sure. Stop me if it's not. But angular frequency over angular wave number is literally equivalent to wavelength times frequency. It's all meters per second, no matter how you slice it. So that V equals lambda f. Now that's specific to waves. First of all, it's always true that for any wave, it's wavelength meters per cycle times its frequency, cycles per second. The cycles will cancel, and you have meters per second. Wavelength times frequency is always the speed of a wave. But what I'm also arguing is that the speed of the wave is fixed relative to its medium. Relative to its medium. So what this front page is saying is that the velocity of a wave is its wavelength times its frequency, but that's like a relative concept. You could say the velocity of the wave relative to the medium equals the wavelength of the wave relative to the medium times the frequency of the wave relative to the medium. Or you could substitute other things. You could say the velocity of the wave relative to some source is equal to the wavelength of the wave relative to some source times the frequency of the wave relative to some source. Or receiver. Like, you could substitute any letters you want in the for W and M, and the statement, as long as you're consistent, the statement will still be true. Okay, this is getting abstract. I'm going to put this into practice in the problem, like right now, for the next 20 minutes. But what I'm trying to say as a general picture is that the Doppler effect is what happens when the relative nature of velocity when the relational character of velocity in general is applied specifically to a wave. The Doppler effect occurs when one wave travels from a source to a receiver, and either the receiver or the source is moving relative to the wave's medium. That's when the Doppler effect occurs. Two things are at play: the nature of wave motion and the relative nature of motion in general. Both, right? So I think the best thing for me to, I'm getting very abstract. So I'm going to show you how to, I don't think I did this last time for your class. I think you watched the video from so in the other class last Wednesday, I very quickly started analyzing one case of the Doppler effect problem that was assigned for homework 4. What I'm going to do now for 20 minutes is I'm going to do a case for you. I'm going to do a little bit more slowly and carefully than I did in the other class, but I'm specifically going to do a different case from the one I did there. So, because what I'm trying to argue for all, you're ultimately responsible for knowing, for being able to solve all 4 cases of a Doppler effect problem. You need to be able to solve all 4, and I think it will come up again in a board meeting in lab if it hasn't already. You're going to see that you're going to practice more than once, but you need to be able to do all 4 cases. I'm here to tell you the one method that'll work for every single case. One method, it's not a new equation, it's just literally putting together these equations. It's one method. If you really understand it, and if you understand it, you do it the same way for every single case, but you'll find if you're doing it correctly, you're going to get a different answer for every single case. So I'm going to show you now, I'm going to walk you through how to do it for one of the cases. And again, in last week's class, I think very quickly I did another case. I'll leave it to you to do the rest. And these are all the numbers from the homework 4. Like, so I am solving like half of homework 4 for you. Okay, so so the situation is you have a speaker, right? It's, or you have a source of sound. It's creating sound. So this what's given, pretty much anything in yellow is given. What's given is that the velocity of the wave relative to the medium is 340 meters per second. How is that given? Why is that given? Because we're talking about sound. And with sound, we always know just that it goes at 340 meters per second relative to its medium, i.e. compared to the air. So that's a given. So this speaker is producing some sound that's coming out at 340 meters per second compared to the air that it's traveling through. Then what's also a given is that the frequency of this sound that the speaker is making is 800 hertz. That's just for this particular example. That's like an A flat, basic, like in the middle of a piano. But so the speaker, according to the speaker, relative to the source, the frequency of the wave relative to the source. Notice how I'm always using double subscripts now on purpose because everything is relative. It's the point. So the frequency of the wave relative to the source is 800 hertz. That's a given. And those two numbers are given for all the cases of this problem, right? But then the point is, I think there's 4 different things that could happen. You could have either, in any, why I say there's 4 cases. So the source is making some sound, an 800 hertz sound. It's coming out of the source, and then an ear, a receiver, is eventually hearing this sound. Now, if the source and the receiver were just sitting there in the air, then it's just a normal propagation of a wave. If everybody's just sitting still, then there's no reason for a Doppler effect. The source would measure an 800 hertz frequency, basically a middle A. The receiver would receive an 800 hertz frequency. It would hear a middle A. That'd be it. But if either of these two things is moving relative to the air, then we're going to have a Doppler effect. What I mean by a Doppler effect is if either one of these is moving relative to the air, that means that even though everybody will agree on what the sound is doing relative to the air, if anybody's moving relative to the air, then from their perspective, the air is moving relative to them. And the sound is moving through a box that's moving relative to them. So in other words, yes, everybody in the world agrees that sound goes 340 meters per second relative to air. But if the air is rushing by you or away from you, then for you, the sound isn't going 340. You see, and I hope you can get your mind around that. Like, again, that's not something we can do with baseballs, baseballs just have their speed relative to observers. They're not fixed to a medium. But a sound pulse is fixed to the air. I mean, it's traveling, is fixed to the air. So if you move the air, you move the sound pulse, like literally. So in the if you have a speaker and a receiver here, when I keep talking about four cases, I mean either the receiver could be the receiver could be approaching the source, or the receiver could be receding, moving away from the source, or the source could be approaching the receiver, or the source could be receding from the receiver. The four obvious permutations, not obvious, but the four possible cases of motion relative to the air. And I'm saying if any of those cases occur, then the source and the receiver will not agree on velocity. They won't. They'll both, like, they won't experience the same velocity of the sound. But they will agree on wavelength. Like, however far apart the sound crests are when they come out of speaker, that's how far apart they will be measured by the receiver. Like just like in the ocean. I mean, if you're like I was sort of yelling before, if you watch ripples in the ocean, it doesn't matter whether you run into the water or run away from the water, or the ship that's making the ripples is coming toward you or away. Like, you and the ship will definitely agree on how far apart those ripples are, no matter what the ship is doing or you. Like, a meter is a meter is a meter, right? So wavelength, everybody will agree on. But if you're running into those waves at the ocean, then they're coming. If you're running into the waves, then they're coming to you faster than they're leaving the boat. That didn't say that well, but if the boat is producing waves and the boat's just sitting there in the water and producing waves, and it's like, oh, look at those waves, they're going 50 meters per second, but you're running into the waves at 5 meters per second, right? And then it's like a head-on collision with the waves. Of course, speed is relative. Relative to you, the waves will be going 55, not 50. And therefore, if you think about it, they will slam you in the face more often than they leave the boat. I'm saying ultimately, or I'll get to the numbers because I'm starting to run out of time. I'm saying what the Doppler effect is a situation where if either the source or the receiver has velocity relative to the medium, then the source and the receiver will not agree. They'll get different measurements for the wave speed, and both measurements will be correct. And since they'll get the same measurements for wave length, they'll have to get different measurements for the wave frequency, which means the pitch of the sound that is sent will not be the pitch of the sound that is heard. You might play a middle A in your car, but if your car is moving past someone else on the road, or they're coming toward you, they're going to hear something different from middle A. That's what I'm saying. So the point of every Doppler effect is to take all the given information and solve for, notice here in blue, our goal is to solve for the frequency of the wave as measured by the receiver. That is the question, step 2. The question is what, and so step 1 is all these givens, is this picture. And the other givens here are, I'm doing a certain case, I'm doing the source approach case. So I'm doing a case where the source is moving toward the receiver at 80 meters per second. Again, I've taken these numbers from homework 4. I'm just doing one of the cases here of homework 4. The source is moving toward the receiver at 80 meters per second. The receiver, and that means literally VSM, the velocity of the source relative to the medium, like the source is moving through the air at 80 meters per second toward that receiver. The receiver is sitting there in the air. So velocity of receiver relative to medium is 0 meters per second. And so those are the givens. Again, the 80 and the 0 that I just said, those would be different for every one of the 4 cases. Like in another case, it might be negative 80 and 0. In another case, it would be 0 and positive 80. In another case, it'd be 0 and negative 80, if that makes sense. But no matter what case I'm doing, I always designate the direction of the wave as positive. Like whatever direction the wave is going from source to receiver, I make that positive, hence the blue arrow that says positive. So now, okay, I know we have 11 minutes left. My goal with these numbers is to predict what frequency is measured for this wave by the receiver. I know FWS is 800 hertz, but I believe that since the source is moving toward the receiver while it makes the sound, this is like the motorcycle on the street, like business. I believe the speaker is measuring an 800 hertz sound in middle A or whatever. Or it's not middle A. I mean, one octave up from it. Middle A is 440. So this is like one octave up. Sorry, not that it matters, but so I believe that the speaker is making a sound that the speaker hears, but it's going toward the receiver while it does that. So I believe the receiver is going to get these wave crests more often, more frequently than they're leaving the source. So the receiver is going to get some kind of FWR that I believe will be higher than the FWS. The question is exactly what number will it get? Here's how to do it. And this procedure I'm showing you right now, and of course I'm going to upload this PDF to you, the procedure is exactly the same procedure for every case. So here's what you do. So this is all like, right, if this were a Doppler effect problem, step one is here's the diagram and the facts. Step two is what's the question? The question is what's FWR? And step three is these are the principles for step three, okay? So now in step four, I start to get to work, and for every Doppler effect problem, I can divide step four into three substeps, A, B, and C, always the same. Step A, solve for the wavelength of the wave relative to the source. I'm always going to get the wavelength according to the source first. How? Well, velocity of a wave is wavelength times frequency, and I want the wavelength of the source. So I'm putting S's everywhere. I'm just being consistent. Velocity of the wave relative to source equals wavelength of wave relative to source times frequency of wave relative to source. So I divide both sides. So the wavelength of the wave divided relative to source is velocity divided by frequency. Okay, so what's the problem? The thing that you have to think about in every one of these cases, the key to the whole thing is VWS. I mean, this is where the subscripts matter. VWS is not just any velocity. It's a velocity that you need. It's the velocity of the wave according to the source, but it's not the velocity that was given in the problem. What was given always is the velocity of the wave relative to the medium. That's what we can know. We know what speed it's doing relative to air. What's it doing relative to the speaker or the receiver? Well, that depends what they're doing in the air. In other words, VWS was not given, neither was VWR. What's given is VWM. So how do you get VWS? You do Galileo's principle of relativity, form number 4, case 3. The thing I was saying, in other words, VWS, the velocity of the wave relative to the source, is equal to the velocity of the wave relative to the medium, which we know, plus the velocity of the medium relative to the source. This is literally the subway thing. It just sounds more abstract because we're talking about waves now. But velocity of me relative to subway plus subway relative to street equals me relative to street. Same thing here. Velocity of the wave relative to the speaker is the velocity of the wave relative to air plus the velocity of the air relative to the speaker, right? That's what we're saying. So the velocity of the wave relative to air is 340 meters per second. So what's the velocity of the air, of the medium relative to the source, BMS? Do I know that? Well, not exactly. I don't know that, but I do know I was given at the beginning of the problem that the velocity of the source relative to the medium is positive 80 meters per second, right? The speaker is going through the medium, through the air at 80 meters per second, like that way. Therefore, case 2 of GPR form 5, case 2 is that the velocity of the medium relative to the source must be going the other way, negative 80, right? If the source is going through the air at 80, then the source observes the air coming toward it at negative 80, right? And so the velocity of the wave relative to the source is wave relative to medium plus medium to source, 340 plus negative 80. And you do all the way. You don't memorize how to do the negative signs and the positive signs. You use all of the negative and positive signs are all based on they're all logically inferable from just making the decision right at the beginning that whatever the direction of the wave is, that is positive. And whatever's against it is negative. Like that's what I'm always doing. So therefore, the velocity of the wave relative to the source is 260 meters per second, right? Like that's not like the final answer to the whole question, but that's an important piece of information. And just like intuitively think about it, I'm just saying if the speaker's running through the air while it could be you in a car, whatever. If the source of the sound, it's making a sound, but it's running through the air while it makes that sound, the sound is leaving it it's like running after the sound at 80 meters per second. So every second, the sound goes through the air at 340 meters. But during that time, the speaker moves forward in the air 80 meters. So the sound is only 260 meters ahead of it. That's all we're saying. Like it was, right? I mean, I think it makes, and that's not that's just old physics being applied to waves here. So anyway, the velocity of the wave relative to the source is 260 meters per second. Now, I did all that work, and you have to do that every time, every case you do that. In 2 out of 4 of the cases, one of these terms might be a zero. Like in the example I did on the video from last week, if you do a situation where the receiver's coming in or going out, then the velocity of the medium relative to the source will be zero. Like sometimes the number is zero, so it doesn't look like any kind of hard math or anything you have to think about, but you're still doing it. So anyway, so why did you do it? Because now we could say the wavelength of the wave relative to the source is the velocity of the wave relative to the source divided by the frequency of the wave relative to the source. So 260 we now got divided by 800. So we get that the wavelength of the wave is 0.325 meters. That's the key. Now again, in the other case where the source wasn't moving, you would get a different wavelength. That's okay. Then that's okay. But that's why you have to do this work to get the different numbers. But we get here that the wavelength of the wave relative to the source is 0.325 meters. In effect, because the thing is moving forward while it creates waves, it creates a crest and then it runs towards it. And then it creates another crest and then it runs toward it. So the crests are closer together than they would be if it was just sitting still. That's what we're really saying here. But anyway, so we get 3 points. So now we go to substep. I know we have 3 minutes. We've done the hard part. Substep B, every single time we just say the wavelength, the reason we got the wavelength first, the reason we got the wavelength according to source is that's the one thing everybody will agree on. In every case, I'm not saying all the cases will get the same wavelength, but I'm saying in any case, the source and the receiver will agree on the wavelength. WR wavelength equals WS wavelength. They're the same. And that's all you have to say for substep B. Now we go to substep C, the last step. We now use that wave, like we can now say, fine, now I can analyze the receiver, which is where I want my answer. I'm looking for the frequency according to the receiver. So what will I do? Take the velocity according to the receiver and divide by the wavelength according to receiver. I'm literally doing the same thing I did in step A, I'm just flipping it. In step A, I used frequency and velocity to get wavelength. Now I'm using wavelength and velocity to get frequency. You might say, wait, aren't you going in circles? Why aren't you just doing the same thing backwards? Yes, except the key is that the velocities are definitely not going to be the same in step A and step C. The whole point of the Doppler effect is that the velocity of the wave according to the source is not the same as the velocity of the wave according to the receiver because velocity is relative. So we do so what's VWR? Same logic. VWR we don't explicitly know, but it's VWM plus VMR. What's VMR in this case? Medium relative to receiver? Well, the receiver's just sitting there in the air. So that's a zero. See, in the other 2 cases, or the case from last week, it would have been in step A that we got a zero. There's always a zero somewhere. It's whether it's step A or step C. But okay, here it's step C. So in other words, to the receiver, the velocity is just coming in at 340 meters per second because the receiver is just sitting there in the air. So, okay, so we just take that 340 and we divide by the wavelength that we just figured out. And guess what? We get a frequency that is higher than 800. It's 1046 hertz. Again, even though it looks like we went in circles, when you really stop and practice this on your own, you'll feel, if you do it right, you'll feel for a minute that you're just doing the same thing twice, like once backwards. But you have every single time you do it, you'll have a different V in step A and step C because in one of those steps, it will be 340 plus 0. And the other, it won't. And it's logic that will allow you to figure out which one which. Okay. And so that's how you do a Doppler effect. You do it the exact that way for all the cases. It's literally just Galileo's principle of relativity being applied to wave motion. But bottom line, what this means is the guy plays like an A and the other person hears, like, let's say an A sharp or a B, if you know what that means. And they're both right. If you took tape recorders and put them next to it, they play different notes. They're both equal because wave speed is relative. Okay. That's class. I will see you in 2 days. Thank you for being so patient. And thank you. Okay. Thank you.